Okay, next we're going to recreate the plots that we made earlier, but we're gonna label them L for light, and that means really the what we've done so far. We assumed the pulley had a mass, but it was a light mass. Okay, so you can just copy those plot switches again, and we're gonna label it as L, what we did so far. Okay, and now next thing is step 26.27, and we're gonna think about what if the pulley was heavier. Would that make any difference? Okay, because before this chapter we assumed the pulleys were ideal. And what was that mean? That mean pulleys had no mass, right, and also had no friction. They're still frictionless, but now they have mass. Okay, so they're not ideal though. And now we are looking at the effect, because when they were ideal, they had no effect on our problem, right? Except to change the direction of the tension and such. But now they are doing something else, and we are investigating that. So if you assume the same stuff, okay, what we done so far today, but you have a heavier pulley, how would your plots change? The first part is this row is all about linear motion, so that's for the hanging mass, and this is for the pulley, so that these are the rotational motion. Okay, but we again have the position and then velocity and acceleration plots. So if the pulley was heavier, think about that, like kind of put yourself in that hanging mass. You're holding the string and there's a pulley, but it's much heavier, so you're pulling it, but it's not as easy as it was to rotate the pulley, right? So you're gonna have a you are going to be able to change the speed of the pulley. So it starts from 0, but it's gonna spin, but it's gonna be much slower because it has more resistance, right? Remember the when we talk about mass, we talked about as inertia, right? So that's kind of how much resistance you have to change to change your motion. And so massier pulley will create more resistance, and we will talk about in the rotational cases, we will talk about inertia soon, but I want you to kind of relate to that as well. So yeah, that's why the acceleration is going to be less, still constant though, right? So this is the reason we have this heavy case at the bottom of the light pulley case. It still has an acceleration, but it has less rate. So the change in speed is not as high as the light pulley case, and you can see that from the velocity case. And these are all about the hanging mass. Okay, this is the velocity of the hanging mass, and the position again is going to be less, so it's not going to go as far for given the same time interval. And in terms of the pulley, again, we have the similar cases. Angular acceleration this time is going to be less. Angular velocity is going to increase, but at a less rate. And that's the angular acceleration. That's the rate. And the angular position, again, will change, but it's not going to be as much as the light pulley case. Okay. So as what we see now is we do have a significant change, right? When we have the mass of a pulley. It used to not affect our problem in terms of those plots, but now it is affecting, and it depends on its mass as well. Okay, and so then in step 26.30 we can summarize this. Did changing the pulley's mass make a difference? And yes, it did. And we must learn when a pulley will have an effect and when it won't. And again, the key thing here is the mass of the pulley. Okay, and we are no longer saying that pulleys are ideal because they will have a mass, but you can always say in this class the pulleys don't have friction. Okay, they're frictionless pulleys still. Okay, so the next is it's a summary, and I put a star next to it because it's very important, and I'm going to explain a little bit more detail than here. But let's just go over the steps that we seen so far. So rotational motion is very similar to translational motion or linear motion. Hopefully you can see that by now. And the position x is simply replaced by angular position theta. X goes to theta, that's the mapping. The velocity v is replaced by the angular velocity omega, and acceleration is replaced by the angular acceleration alpha. The angular variables are related via derivative relations, just like translational variables, as I showed it in my review, the first video. And we can consider cases where the angular acceleration is constant and we generate equations very similar in form to 1D translational motion with constant acceleration. They're still vectors, but there's a little difference, so we are a little bit sloppy on the vector notations, but that's why we kind of want to use 1D to relate things, because we didn't know, in chapter 2, we didn't know vectors, right? But it's very similar relation. And angular variables are vectors just like the translational variables are. And if omega and alpha, so velocity and acceleration, but angular, have the same sign, then the object speeds up. Right? If they have opposite signs, then the object slows down, and there were some clicker questions from last time, so hopefully they are clear too. So